Hello guys. So this is the second video uh, of how to use movie library to optimize the neural network. And in this case, we're gonna try to optimize the hyperparameter of the neural network, right? Okay, so let's get started. In previous video, we got the traditional neural network for time series problems. So now we're gonna try to use this to optimize the hyperparameter of this model. Okay, so the code of the traditional code you can find in this link, is available in this link. Alright, so now we need to know what hyperparameter of the neural network we would like to optimize. Okay, so let's search on internet. Okay, let's search it on. Okay, uh, training hyperparameter neural network machine learning mastery. I found it in article. It describes very very detailed about the the hyperparameter of the neural network. So we're gonna try to optimize some of them like here, some of them here. Okay, so let's get started. So we uh, in this article he used he used Griswold method to find the best model, right? But the Griswold method is like a proof of method. It means that you uh, try to find the best model based on own combination of set of parameter. So, but we don't want to do that. We want to use meta heuristic to find the best model. Okay, so in the neural network we have pass size and chaining epoch. Okay, okay, let's get back to the traditional code. Okay, so here is a traditional code, right? So let's delete this also. Here is a traditional code. So now I would like to optimize the first one, the uh, batch size training. Second should be epoch training, right? Legit batch size and training and optimizer. So should be optimizer. Fourth should be learning rate and momentum. Okay, so because optimizer they have different learning rate and they also don't have doesn't have momentum, so we're not gonna try to optimize this. We're gonna try to optimize learning rate only. So should be learning rates, should be network weight into initialization, and should be activation function. Okay, so all right, activation function. Okay, 7 should be no 12 we don't want to do this. Okay, then the number of the neuron in hidden layer. So with assumption that we are trying to we are trying to optimize the multi-layer perceptron with 3 layers, one input, one hidden, and one output. Okay, so and Okay, so the number of hidden units. Okay, so we have 7 variable for this if if you guys want to optimize the number of hidden layer, the number of hidden layer, number of hidden layer, also number of hidden nodes in each layer. That is a difficult task. It can be done. But it is very difficult because why I said that, because for let me explain. So we are trying to find the best model, right? Best model based on this configuration. Okay, so here a solution for this problem should be x1, x2, x3, x4, 5, 6, 7, and 8, and x7. So x1 is for the best side, x2 is for the epoch, x3 is for the optimizer, and so on. So now you are trying, if you want to optimize also the number of hidden layer right here. Okay, let's just say we got a guess, but you have to also have to optimize the number of hidden node in that layer, in that layer. Let's just say that we found, for example, for the solution, first solution, we found the best number of hidden layers is hidden layer equal to 2, right? So we need to find a solution. We need to find the number of hidden nodes in each layer. So we need to expand this solution with x9, x10, right? In which x9 equal to the number of hidden units of layer 1, right? And x10 the number of hidden units layer 2, right? Because we got 2 hidden layer here. Alright, so for this solution we need to expand this solution for the first solution. But now, for example, we got the second solution with hidden layer equal to 4. So we need to expand to the solution. Expand this solution is 11, 12. So in, you see that? Do you understand? So but in meta heuristic process, you cannot expand the solution. I mean the number of dimension efficient before and after the meta heuristic process. So you actually cannot do that. You cannot optimize the number. You are not able to optimize the number of hidden layer with hidden node inside each layer. But you still have a way to do that, like it. So let's just say that a solution like this. Okay, we have a solution like this. So the x7, I mean x should be the number of hidden layer, right? And x7 should be the number of hidden nodes in each layer, meaning that all hidden layer have the same number of hidden nodes, so you don't have to expand the solution anymore. So you can do that, but the negative of this method is that each hidden layer you will have the same number of hidden nodes. So maybe that is not good, right? Not good enough for the model. So, or another way, you still have another way to do it, right? Another way. Usually maybe it's a better one you want to try. So for example, I limit I limit the number of hidden layer to 5 layer. Okay, so the number of hidden layer belong from 1 to 5. Okay, so uh, so you will have a solution like this. You will have a solution like this. X 9 x 10. So x is for the number of hidden layer. X is number of hidden layer. Okay, and x9 should be x9 should be number of the number of first hidden layer, number of hidden units in the first hidden layer, and then again in second hidden layer, and 11 should be third hidden layer, 12 hidden layer, and 30 should be fifth hidden layer, right? So we will have 11, 12, 13, 14, and okay, 13, right? That's just okay. So you will have to organize a solution like this, and if you found a solution, let design first. Wait. And third way. Not the third way, and the second way. So if a solution you found if you found a solution with h equal to 2 hidden layer. Okay, so you will have you will take you will take two value x9 and x10, right? x9 and x10, and then ignore other value 11, 12, 13. Alright, so you will have to ignore these three values. But the disadvantage of this method is that if we have a solution, such as we have a solution one like this, okay, such as 12, 10, 10, 10. Just say it is 5, 50, 100, 50, and then 10, 10, and then solution 2 equal the same, but only the difference between in the 13, like 20, or we have a solution 3, solution 3 like it. So you see, because we ignore the value of 11, 12, and 13, so all these three solution will give us the same result. I mean that they are identical, right? Because we are ignore all these three value. Okay, so even that the 13 value is different, but all three solution here is identical. So that is the negative or disadvantage of this method. But that is the way how you decode, or I mean how you organize a solution for this problem, right? So let's try let's ignore this, ignore the number of hidden layer. Okay, so let's try to optimize the other hyperparameter first. All right, so we have 7 hyperparameter with the assumption like this. Okay, so let's try to do it. Okay, let's create a new file and name it hyperparameter MLP. Okay, no, hey, MLP or meta heuristic algorithm hyperparameter MLP. Okay, for time series. Alright, let's go. Let's copy the code of the traditional time series. Okay, and let's go with we actually don't need to create a class like the optimize replace the gradient descent algorithm. So we just give a function. So we, like I said before, we need 4 things. Let's get back to here. Where? Here. We need 4 things. primitive function or objective function, lower bound, upper bound of variable, mean or max problem, number of dimension, right? So let's start. Let's design an objective function, and we will pass a solution into it, right? So I think we should define or declare the lower bound and upper bound for each dimension here. In this case, in this problem we have 7 dimensions, right? Each dimension is inside a solution like this. So for path size training, right? Okay, so the rules. Let's make the rules for path size. Alright. Path size it will take from it, because we don't have in the problem we don't have much data set, much data example, so just use more path size like 2, 4, 8. Alright, like this. Or for a bigger problem you can use like 64, 1 to h to the 5 6, and 5 1 2, like this, and so on. So but the problem is so small, so it should be this. Second epoch, okay. This should be around from I think from 700 to 2000. Oh, that is enough. And for optimizer, okay, for optimizer we can see from here. Optimizer, I go from here. So for the optimizer, let's see, have maybe we can search the optimizer in gas, right? Alright, so or we can search from here. Training optimizer algorithm. Okay, so here we have optimizer right here. Okay, copy this, or you can check it from here. We have optimizer class. So with HGD, RMS prof, ADAM, ADelta, ADagrad, ADAMAS, NADAM, and Actual. So, or we can check copy paste from here. Okay. For the rule for optimizer, lower bound and upper bound. Okay. So for is loading rate, so we should loading rate should run from 0.01 to 0.1, right? Or 0.5. I think let make it as a real number. This should be real number, not okay, real number. Just real number. Q4 should be network with internet initialization, right? Okay, let's see. Check it for network with initialization. Okay, so here we got this right here. the mode for initialization with a lot of mode, right? Should be activation function. For activation function, all right, we have activation function, and so we have number of hidden units. Number hidden units. Let's just say from 5 hidden to 50, right, or 100, and this should be integer number. All right. So we have the rules. From here we can create lower bound and upper bound for it, right? So now we have the lower bound and upper bound. This is done. We need to, and the problem we are trying to solve is minimization, right? Because the load function we use is mean square arrow like this one, okay? So minimization problem, and we need to design the finite function. So we already know that there are 7 dimensions. Now we need to know the finite function. We need to design the finite function, alright, or objective function. Okay, let's go. So right here we have bus size equal to, so let's design lower bound should be, and upper bound should be an array. The lower bound for the first element should be from where? I think it should be from 0 to 0 to 1 to 2.99. Why is that? Okay, let me explain. So the pass side, go to the solution. The solution with the index 0. Okay, so because we know that the solution, it will return the real number. Okay, so now we need to make it as an integer number, right? Because the pass sign is an integer number, right? 2, 4, 8, and it is the exponential of 2, so you can use so if this solution return, if this value return is 0, we have 0 minus exponential 1 to 0, so it should be 2 exponential just 1, and if it return 2, right, it will return 2 minus 2 exponential 2 equal to 4, and 3 exponential 3 equal to 8, right? So we should return the value, return the value from 1, 2, and 3, right? So the lower bound should be 1, and the upper bound should be 3.99. Why is that? Because if this value, if this solution return value from 1 to 1.99, it will return as 1. But if this solution index 0 return the value from 2 to 2.99, it will return the value 2, and from 3 to 399, 3.99. It will return value of 3. Okay. So what about if this solution returns the value of like such as 0.5? It will never happen because we got the lower bound is 1, so it's always return the value inside this range, so we don't have to worry about it. All right, so you know how we do it, you know how we design the value for the first dimension, back side dimension. All right, so let's go to the next one. So for the epoch we do it the same, and epoch it should be 100 minus in solution 1. So the lower power for epoch should form what? 7, right? Because 100 minus 7 equal to 7, and upper power should be, the mark value should be 2000, so it should be 20, but it should be 2000. So the upper bound it should be 20.99, right? You understand that? It is the same as above. So okay, done with epoch. So for the optimizer, all right, for the optimizer, okay, so because the optimizer we need to return the we need to transform the real number or the real number into a string. So how we gonna do it? So we have to we there another way, a way to do it with label encoder from scikit-learn module preprocessing, and we will import label encoder. This class they will transform a string into an integer or reverse. So that is what we want to do. So let's design. Let's make an label encoder right here. Label encoder for this one is optimizer. Okay. Encoder. All right. It should be label encoder. We create an object, and we fit of encoder. We fit with the value right here. So we fit the value at an arrays, Python arrays. So, and now you can try to print right now. You can try to print now optimizer encoder dot value. I think not dot value. I mean, so they will assign each string value here. Maybe I said maybe, alright. HGD it will assign with number 1, and RMS Pro it may be assigned with number 3, and so on. Okay, and so on. So now if we have the value the integer value, we can reverse it back into the string value like this. Okay, using the function inverse transform, and the value you put it maybe from 1, so this will return HGD string, right? So okay, we need ops uh, ops integer should be in solution 2. Alright, so now we have a solution because in this domain range we have this domain range we have 7 value, 2 4 6 7 value. So and this kernel and this optimizer because they index from 0, so we actually had the lower bound should be 0 and upper bound should be 6.99. I hope you understand. So from here we can try to get the optimizer of should be of encoder and inverse transform from of integer, right? So and because this function they return a list, so we need to get the first element. Okay, so now you have the op should be one of these values. So if solution return at 0 to 0.99, we got the 0 index, and it should be HGD H47, and from 1 to 1.99 it should return 1 index, and it should be the LS Pro, something like this, right? Alright, so say that it comes from 0 and let's say it comes from 1. Okay, so for other string like network web initialization, you do it the same, like the same, and activation function you also do it like the same as optimizer. So for the learning rate, the low bound should be 0.01 and the upper bound should be 0.5. And we will do it to the network wedge initialization. So let me check with optimization initialization encoder label encoder and we have wedge dot fit. We fit, okay, but with the value, yeah, fit the value, we fit the value, remove this, we fit the value here, okay. Let's try to do with activation. Right. Encoder, we go to label encoder and add encoder dot fit. We fit the value right here. Alright, so and so now we got this. So for learning rate equal to solution 3, right? And network with interaction network with initial equal to in solution 4. Okay. Initial should be integer and alright. Okay, so initial equal to here should be inverse transform with integer, and we got the third element, right? You understand that? Okay, let's go to activation h integer be shows with 5, and activation should be into the inverse transform integer go from top down, and number of hidden units should be in from solution. So let's get back to low bound and upper bound. So lower bound for 1, 2, 3, 4, 5. The fifth element minute weight should be from where? From 0 to network weight. We got 1, 2, 3, 4, 5, 6, 7, 8. So 8, right? Or 7, right? 7. I mean 7. 7.99. So for activation, we got 1, 2, 3, 4, 5, 6, 7, 8. Also from 0 to 7.99. For hidden layer, for hidden unit, we got from 5 to 100, right? 5 to 100. Okay, so we finish the low bound, and this should be from 6. Alright, so we have everything we need. So now we need to run the neural network inside the objective function. Here we should copy this. We define the model with the number of hidden units should be number of hidden units. Activation function should be activation, right? And the number the optimizer should be optimizer right here and the load function. Okay, we actually we didn't we haven't optimized. We don't want to optimize load function. We just use this one. So we latch a pass sign h y up from here. Learning it. Okay. So I think it is from here, right? run red equal to run red. Okay, so web initialization. Let's see where did it come from. Okay, so where this guy. Okay, init mode right here. Init mode and kernel initialization like this. Alright, so we need to copy this in this dance class, right? Alright. Mode should be web initial, and for the pass side, let's go to pass side. Alright, it come from okay, too much. Right here, debox and pass side. Define here pass side equal to pass side. Anything else? So hidden activation, learning back, optimize. Oh, okay, that all. Oh, okay, that all. Happy now. Alright, so now we got the result, the training, but we actually don't want to use the training result to select the best model, right? We usually use validation set to find the optimal parameter. So in this case, the test set, right? So let's design the training and the testing set, right? So here is our data set. Let's create more. Alright, so the chain, test, y test. Okay, I'll take 60% for training and 40% for testing, right? So it should be from 0 to 12 because 60 plus 60 multiply 20 should be 12, and here from 12 to 0, I mean from to the end or to 20. Okay, so put this about put this about. Okay, so now we have everything for this card, right? So only thing we need to do is white chain, chain and white chain, right? So let's do this. Let's go chain and white chain right here, and then we trying to uh, predict the test and white test. Okay. Or let's just use let me see. Let me see how to get the accuracy or the load value of the model. Yeah, I don't see it here. How the hell they still running? Alright, so maybe we should be now the model not history. I think so. Oh, we should check the loss value of validation test. Set apps. Finish value for selecting the best model. Right. Okay. So we got the hard model dot predicts. This should be its test and don't need this actually. Don't need this. Maybe. Now we should find the finish equal to the finish by on the mean square error. We need to import the mean square error method from sklearn dot magic import mean square error function, and we code it from here with y2 the y test and y hat is prediction, and we should return the finite value. Alright, so try to run it. So we have everything. We don't need this, okay, and we also don't need this. So now we need to we need to define the model or import the model we want to use. Let's use formula dot swarm by. Let's use very wolf optimizer, right? So model equal very wolf optimizer dot by optimizer problem debug equal to, like, I want to try to find apple size equal to 50. Okay, so we need to define the problem dictionary. Okay, I'll copy from here. Okay, I'll copy from my sample right here. I'll copy the problem dictionary. So objective function, we have the objective function right here, and low bound, we have low bound right here. Nice. Upper bound, we have upper bound right here. and this should be minimization problem. We want to print out the training process. Okay, and we go to solve function. Solve function. Now we want to print out the best solution. You can call it for model.solution and get the first element. The first element is the solution, the best solution. Okay, so now if you want to find the best model, you have to call all of it again, right? You have to call all of it again, like, okay, let's copy this one more time. Copy it down here, copy it down here, copy right down here. Okay, so I think you can, what you can do is you can write down a decode function. Write down up here, decode function, decode solution. Alright, so we have the solution, and we would like to get the real value. Let's return pass sign equal of language network webs initialize activation and hidden changes, right? So you can comment it down, right? You can comment it down and call the function equal to cell dot equal to decode function. Okay, alright, so like this. So that should be easier. And now you can go it one more time, right down here. Right down here. The solution should be model.solution dot 10. Okay, so now you can print pass sign equals should be of learning this should be learning this, and another one. What is this? Network width initialize. Activation should be activation. Hidden. And hidden. Alright, so okay. So I think that all. Okay, now to try to run it. Let's see. Do we have any errors? Okay, so we have the errors. Invalid key argument in combine method, learning rate and pass sign. It means that for this check your define objective function, right? So maybe for this optimizer, I think so. Maybe for this optimizer, is the not receive the learning rate and pass sign. like this. Compare. Oh, I think. Oh my gosh, I don't know. But let's see. Does it actually do that? Optimizer and level. Try. Okay, so. Oh my gosh, so he created a real optimizer. And if that is inside here, learn rate and when to. So they know bad side. Okay, I get this. Alright. So how about bad side? Bad side. I'll turn bad side. Okay, model. Oh, so they actually call the bad side inside the feed function, not combine function. So we have bad side right here. Should be here. Alright. All the bits did not from here. So I think we should have let's go to the optimizer. Where is it optimizer come from? Okay, do this. Okay, so that is how they compile the model, right? So let's copy it, and we will get. Okay, so where did actually come from? We from Keras optimizer HD. Okay, from Keras. So we should import from Keras. Nos model import. Not model. Uh, optimizer. Oh, we should import optimizer, right? We should import zip file. I think so. Yes, optimizer. Import was. Oh, so they got everything here. Alright, optimizer. Do this. Yes, import optimizer, and we can get it. I think we can get it by the string value like this. By from we got optimizer should be get attribute right like this from optimizer class optimizer file, and we get by the name optimizer our optimizer of name of, and then we create an object with the learning rate magic one. learning rate logic 1 equal to learning rate. Alright, and then we pass the optimizer into this one or here right here, and we actually don't need learning rate right here. Okay, so I think that will work. Let's try. Alright, so it working. Nice. Alright, so I'm running for and get the error like this. I think maybe because we put the number of hidden units too large. So let's try to reduce the number of hidden units to 50, right? So and we also don't want to print out all things like this. So let's try to set the workload equal to 0. Try to run it again. What the hell no? What happened? Okay, so I run the code and I missed the problem because the finish function it returns the infinite value. So I think because the value we are trying to put into the network is the raw value, so we should using scaling method like min-max scaling to make it smaller back into the range of 0 and 1, right? So to do that we can import the min-max scaling from scalar dot preprocessing, and we use scalar sequence equal to min-max scalar. Let's define a scalar equals min-max scalar. Let's create an object and let's call the scalar. You can search the min-max scalar from here. Yes, min-max scalar scalar, and it will show you right here the example for this. Alright, so we need to create an object and we feed and we transform the data. So we have scalar sequence equal to scalar dot feed transform. We feed and transform at the same time, right? So with the raw sequence, let's see, and then here we need to use the scalar sequence. Okay, so the sequence, the arrows happen because in the fiction form here they require the magic or 2D array, so we need to reset this sequence. Let's import the reset function from numpy, and let's reset this sequence in arcs and rows and one column, right? So and then we need to flatten back into a single array because we are trying to get the value from like an array, not a magic. Alright, so it's working. So let's see. Okay, so warning. Let's try to turn off this warning. Okay, so let's copy it and search. Copy and search. Okay, so I found this. Solution. This guy said that he also trying to use time series and breed new inside the loop like we did. So the solution for this, yeah, he said that we try to remove the function replace this function by the model of this function only. So in the loop function here, right here. So what we can do is we don't need this. Insert do this, right? Model H, right? So that, and we should reduce the number into 20. We want to see the result. Okay. So now we are waiting for the result. I hope we don't get any errors anymore. So code is running, actually running right now. Because when each solution is created, it will call the objective function. In the objective function, they will create a new neural network and training that neural network and predict thing with that thing data set to get the result. So that's why it takes too much time to finish an epoch of our optimizer, remove optimizer. So let's wait and see the result. Maybe we can try to reduce. Maybe we should try to reduce the number. We can try to reduce the number of value right here like this. We can try to reduce them. So I'm trying to test the network, right? So okay, so we got the result for the first epoch. We got the finite or the log values. The log value of this, the mean square errors of this network is so small. It is nearly like 0. So maybe we got the best model. So it's running, guys. It's running. So now you know how to optimize hyperparameter of the neural network, right? In this case, it's for time series problem, but for classification problem, like this problem, we can do the same. At a time series problem. Okay, so I keep it up with the result. So we got the best solution right here, and we got best side to epoch 700. Optimizer is ada graph, learning rate is like this, and is uniform activation line here. The number of hidden should be 19. So this is the best result for the best model got. So hopefully you guys understand how to optimize hyperparameter of neural network using Ruby library. So if you guys want to use different optimizer, different meta heuristic algorithm, just import and use it like from Ruby dot evolution knowledge import whatever. One is pollution flower pollination algorithm or something like that, and you do it the same model dot pair dot base pair FPH right? So maximum above equal to same and both sides everything is the same. The same for other optimizer, you can do it, but it's the same. Okay, so I think I will finish the video right here. Thank you for listening, and hope you guys enjoy. Bye bye.